So welcome back. Now we will continue to part B of exercise 1, where we now suppose that u1 is an increasing function, and we want to show that u1 of u2 is a concave function. So what do we know about u1 and u2? Well, about u1 we know that it is increasing, and apart from that we also know that it is concave by assumption. And about u2 we know that u2 is concave. And how can we use this information? Well, we would like to end up showing that given x and z in I, where x is different from z, and any alpha in the open interval between 0 and 1, that u1 of u2 of 1 minus alpha x plus alpha z is greater than equal to the linear combination of u1 composed u2 of x, u1 composed with u2 of z. You get what I mean. So I want to show this. This is what we want to show. So it would be really nice if we were able to use some of what was over here to show some of what is over here. So over here we've got something with u2 and a 1 minus alpha of x, and 1 minus alpha times x and an alpha times z. And over here we've got something with u2 as well. So we might as well just start off by writing up what we know about u2. So by definition of concavity, we know that for x and z different from each other, and for some alpha in the unit interval, that u2 of 1 minus alpha x plus alpha z is greater than or equal to 1 minus alpha u2 of x plus alpha u2 of z. And that just follows extremely simply from the fact that u2 is concave. So we now know as well that u1 is an increasing function, and something we can do with increasing functions is take an increasing transformation of both sides of an inequality and still keep the inequality without changing the direction of it. So that's what we do now. We evaluate u1 in this point relatively this point. So I can just illustrate quickly that since we know that u1 is an increasing function, then if you know that a point y2 is greater than y1, then for an increasing function, you'll know that its value in y2 will be greater than its value in y1, because that's like the definition of what it means to be increasing. So we do this, and then we consider this part where, well, if we can say if u2 of x is different from u2 of z, then we can apply the definition of concavity for u1 and reach this fact. Now note that I can only do this if u2 of x and u2 of z are different from each other, because that's one of the notions that must hold for us in order to use the definition of concavity. So let's just start with this assumption first. Well, if we assume this, then we have actually shown that u1 composed with u2 is a concave function, because what we have over here is u1 composed with u2 evaluated in this linear combination of x and z, and what we have over here is the linear combination of u1 composed with u2. So that's the case if u2 of x is different from u2 of z. Now what if u2 of x is equal to u2 of z? Well, first of all, let's note that that is actually not an unlikely scenario, since even if we choose x and z to be two completely different points, then if u2 looks something like this, for example, it's still quite possible that u2 of x and u2 of z has the same value. But if this should happen, then we can note that all of what is inside here just evaluates to u2 of x. So this thing would be equal to u1 of u2 of x. Yes? And this is again actually just, it doesn't really matter if we split this up into 1 minus alpha part and an alpha part. So this is the same as 1 minus alpha times u1 of u2 of x plus alpha times u1 of u2 of x, and since that was just the same as u2 of x was just the same as u2 of z, I can just write z over here. And then again I've shown concavity, so it doesn't really matter if x is equal, if u2 of x is equal to u2 of z, there's concavity either way. So what we conclude from this is if u1 is concave and increasing and u2 is concave and increasing, then if u1 is concave and increasing and u2 is concave, then u1 composed with u2 is concave and increasing.